So, hello, dear colleagues. I'm glad to see you on our scientific talks by Ukrainian Scientific and Educational IT Society. Today, we are glad to host Olga Russakovsky from Princeton University. And before we start, I want to share some technical details, like people who are on Zoom with us. You can use Q&A button to ask your questions. Yeah, and I believe that a lot of people will watch that recording online, so enjoy that. And I wouldn't steal your time anymore. Olga, please, the floor is yours.
Amazing. Well, thank you. Thank you so much. Thank you so much for inviting me. Thank you for having me. Thank you to everybody who's joining live, and thank you to folks who are watching this afterwards. I live in Princeton, New Jersey now in the US. I'm originally from Kharkiv. I moved before the schools became in Ukrainian. So I studied Ukrainian sort of as a second language, but I primarily speak Russian. And this is, anyways, I have a lot of very deep and very complicated feelings about what's going on right now. And I just want to say that I'm far away. I'm not in Ukraine, but I really, I feel for each and every one of you. I have family in Ukraine. I have family who fought in the war. I have family who were killed in combat. I'm sending all my hopes and prayers to all of you, and I very much hope this nightmare comes to an end soon. And thank you all so much for being here and for continuing to keep up to date with all of the developments in AI, with all of the sort of latest and greatest scientific discoveries, because I think it's so important to maintain that connection and that hope that we will emerge from all of this nightmare, and we'll Ukraine will come back swinging as a very important power with amazing scientific work and scientific discoveries, and will anyways, I just hope this whole nightmare comes to an end. And thank you to each and every one of you for being here, and also for standing up for Ukraine. So with that, I'm going to talk to you about my research, which is completely different, but it also it touches on some very human subjects, some very sort of human questions about visual recognition, about what does it mean to build computer vision systems that are more fair, more representative of the world. So the title of the talk is Fairness in Visual Recognition, and the sort of subtitle is The Importance of the Human Perspective in Computer Vision. So I will, first of all, start by showing a picture of my lab. So these are a number of PhD and undergraduate students and postdocs who are working in my lab. We are the Princeton Visual AI Lab. And I use this picture to illustrate some of what we work on. So we're building computer vision technology that can look at photographs and automatically understand what is in these photos or videos, can look at visual data and understand what's in there. So for example, build object recognition tools that can look at a photograph and say, okay, there's a fireplace in the back there, there's a box of Legos, there's a glass here in the front. Build scene understanding models that understand that these are people who are all sort of sitting around the table. It's a dining scene. Could maybe understand the relationship between different objects. So this is a person who's wearing glasses. The object glasses is sort of connected to this visual concept of person. Can do action detection, so understand that people are sitting, people are smiling, people are posing for a photograph. And of course, this can have a number of applications in various domains where, you have a household robot that's assisting the elderly and wants to monitor sort of this person who's living independently in their home. How are they doing? Are they, sitting down on the floor because they're trying to reach for something, or are they sitting down on the floor because they've fallen and they need help, or are they lying down to go to sleep, or are they lying down again because they've fallen and need help, and so on. So action detection, action recognition comes into play in a lot of those kinds of applications. course, a lot of the recent work in visual recognition is around vision and language. So being able to actually output a natural language, for example, description of a scene, being able to really connect all of the visual components with natural text. And recently, of course, even being able to output a sort of do the reverse of outputting a photorealistic image from a scene. And of course, the work we do in my lab, it's not nearly as good as DALL-E 2 or some of these other models built by companies, but we do some work around trying to understand how these systems, this sort of generative AI models work. So our goal for computer vision systems is to make sure that they are both trustworthy and trusted, where trustworthy is sort of more of a technical computer term, so that these systems are capable and robust. Trusted is more of a human term, where these systems are transparent and responsible. And then I think that sort of at the intersection of those two is this question of like thorough evaluation. So making sure that these systems are actually evaluated in a way that makes it clear sort of under what conditions we can trust them, sort of under what conditions are they actually trustworthy, but also being able to communicate their capabilities to humans. And so, for example, a lot of our research work actually ties sort of across, covers across the spectrum. So, for example, you can pull on this thread of like, are these systems capable? And we started doing, a number of work that starts from trying to improve the capabilities, trying to move them from just systems that can do image classification. So just predict one label per image. Is this a picture of a person, or is this a picture of a glass, or is this a picture of a laptop? But moving towards, vision and language, moving towards descriptions. But then that gets us into a number of questions about like, okay, so how do you measure the actual accuracy of the system? Like, what does it mean to produce an accurate description of an image? How do you think about what should these systems do when they encounter something that they haven't seen before? How do you actually figure out, well, so they're accurate, but are they accurate for the right reasons? So getting into classifier explanations, and then getting into, human trust in this systems. And then similarly, coming from the other side, right? So some of our work on AI fairness, which is what I'll talk about a lot today, is starting from the question of like, are these systems actually responsible? Are they representing everybody? Are they good on the privacy side? Are we sort of protecting the privacy of people, protecting the privacy of individual citizens who maybe have not consented to having their data used in this way? But then all of this sort of comes back to some of the technical questions of like, are these systems fair? Well, how do we think about like, what does it mean for a system to be fair? How do we think about biasing these systems? How do we think about bias propagation? How do we think about, what can we do from a data set perspective? What can we do from the algorithmic perspective? And these sort of more social questions take us into some of the technical, back to some of the technical questions. So let's just kind of ground ourselves when I'm talking about, building an AI system. So first of all, for the rest of this talk, I'm going to assume that like AI is essentially equivalent to machine learning. We can talk about the differences between AI, between artificial intelligence, and the difference in machine learning. But for now, let's just, since most of AI these days is being built on the concepts of machine learning, I'm going to think of them in sort of similar ways. And so basically, there is somebody out there who decides that they're going to build a system to do a particular task, or for example, determine, in the simplest case, or it's not quite the simplest case, but in this day and age, this is, a pretty simple use case for computer vision systems. So they're going to build a system that can determine what objects are in the photograph. So how do you go about that, right? So you collect a set of photographs, you find some annotations for these photos. So you say, okay, these are all pictures of cars, these are all pictures of dogs, these are all pictures of people. So you can do this either through manual labeling, where you hire somebody to look at every picture and provide an annotation, or you perhaps use some of the data on the web, some of the tags that are automatically available on the web, to get this labeled data set. You build some kind of statistical model that learns from this data, learns its parameters from the data, learns the statistical patterns that are associated with each of these tags. And then given, of course, a new image, it's able to run through the model without looking at the training data and output the set of objects that are in the photograph. So a lot of the work in computer vision, a lot of the time when we're thinking about computer vision or machine learning or AI, a lot of the focus is on building the model. So how do we build the latest transformer model? How do we build the latest deep learning model? How do we build, the latest CNN, whatever the latest and greatest model is? But there's actually, if you notice, there's sort of three pieces here, right? So there's the data piece. So there's questions about how do we get this data? How is annotated? Then there's also, of course, questions about the model. So that's one of the pieces here, but it's not the only one. And then there's a piece about humans, so sort of human judgment and who actually participates in this, in the design, who makes some of these decisions. And so I want to acknowledge that when we talk about the human piece of somebody who sort of decides what models to build and how we're going to go about building them. So there's much to be said about power structures here. So who decides what problems to tackle with the next, AI intervention, sort of who proposes and implements AI solutions, who determines and oversees the AI ethics, who governs these systems, so who determines the laws that apply to how we should be building the systems or how we should be deploying them. Who has the resources to contribute to AI research, right? In order to train some of these models, you need millions of GPUs, you need a ton of compute infrastructure. And when we're talking about, a country like Ukraine in the middle of the war with blackouts and, electricity missing from large parts of Ukraine, versus when we're talking about, the need to sustain these giant compute clusters, right? So there's a lot of disparity in the world about who actually has the resources to build these models, which then leads to questions of who then has the power to control what these models are doing, to control how they're going to deploy the models. And then, of course, there's sort of the question, right, of who gets overlooked or who even gets exploited with AI progress. So what are these models, are they doing good in the world? Are they doing bad in the world? How do we think about all of this? And so these are all very important questions, but I'm a computer scientist. I have thoughts on all of these, but this is ultimately sort of not my core research area. And so for the purposes of this talk, let's just focus for now on the extent to which humans, sort of beyond AI researchers, so putting aside some of these questions about power structures, to what extent are humans part of technical AI research? So in order to talk a little bit about that, so let me give a little bit of history of computer vision. So some of this may be very familiar to some of you, some of this may not be, but this is sort of my quick perspective on what's been happening. So I'm going to go by decades, right? So we're going to start, really computer vision started in the 1960s. It actually started as a summer project at MIT. The MIT AI lab was trying to build was working on building AI, and they thought, well, okay, we need to solve this computer vision thing of how do we actually extract information from a photograph? And so they hired a summer undergraduate student to work on this for 3 months. They said, okay, can you in 3 months just figure out how to build a system that can analyze photographs? And of course, the rest is history. This became a huge field that's still unsolved today. But skipping ahead to sort of around the year 2000, so computer vision was basically building models on early benchmarks. So this was, if you may have heard of MNIST or CFAR10 or even or Caltech 101, even Pascal was sort of around that time. So there was pretty little emphasis on the data, so the green part. So a little bit. I mean, there were some data sets. Everybody was sort of using those data sets. There wasn't very much talk about what is actually in that data. A lot of the focus was on building models. So this was sort of the era of Viola Jones. This was the era of hog detectors. This was the era of SIFT. The era of deformable parts models, sort of around that time, and very little conversation about sort of the role of humans, right? It was mostly about really just the modeling. Around the year 2010, so this was the sort of beginning of the era of ImageNet plus deep learning. All right, so the ImageNet data set got collected. This was some of the shift to talking about okay, really the data seems to be, having access to this large scale data then sort of fueled the boom of deep learning. It kind of showcased the power of deep learning methods. And so there started to be kind of more conversations about the data side. And related to the data side, because ImageNet was collected using crowdsourcing, so using sort of humans to actually label all of these images, there started to be more conversation about how do we effectively get humans to help us annotate these large-scale data sets. But it's still primarily sort of the focus on building the models. Around the year 2020, so this is where data really started becoming a first-class citizen. And there were sort of a few things that contributed to this. So one is kind of the growth of concepts like self-supervised learning. Sort of more and more and more people were realizing that like the more data you feed into your algorithm, even if it has imperfect labels or it has no labels or whatever, sort of really learning how to harness this very, very large scale data sets to build better models. So NeurIPS, which is the top computer vision, top machine learning conference, or one of the top machine learning conferences, started having a data sets and benchmarks track where they were really encouraging and sort of centering the work on collecting data sets and collecting benchmarks, sort of really saying that the contributions to the machine learning, to the AI community, is really not just in building these better optimization algorithms or better models, better architectures, but it's also in how we think about collecting data. But around that time, actually, the conversations on the human piece started to shrink because people were starting to say, well, it doesn't matter what the labels are. It sort of doesn't matter. We just grab all the data from the web and that's sort of all that matters. And the conversation around how do we get annotations for the data and things like that were starting to shrink. So I would argue that sort of now, right, this is the inflection point actually to bring back some of these human conversations. So now is a point of transition. And the reason is these systems are becoming really, really good. So these systems are starting to be deployed everywhere. And we've been saying this for years, right, that sort of AI is everywhere. However, it's now actually true. So with all of the, face recognition technology that's being used all over the place in all kinds of applications. So in the US, for example, a lot of the time when you're boarding a flight, they don't actually check your passport or any kind of identification. A lot of the time, they'll just like scan your face and match it to, they'll know who you are. The growth of large language models, right? So ChatGPT, all of these things, there's a boom of this technology being used absolutely everywhere. So that means that now more than ever, we have to really ask these questions of like, okay, so there's some amount of like, importance of data, right? There's importance of models. And then there's the importance of thinking about, okay, so what are these things actually doing in the world? And sort of beyond the AI researchers who are building them, how are they interacting with people in the real world? And then this, of course, raises questions of trusting these systems. This raises questions of, what are they actually doing? What impact are they actually having? And so around the year 2017, there started being conversations, particularly, particularly in the US, in the media, but I think this, to greater or lesser extent, started around the world. So we're seeing headlines like, so computer vision model learns to quote unquote increase attractiveness by manipulating skin color. So what happened there is a company built a photo filter. So when you take a picture of yourself before uploading it to your favorite social media platform, you can sort of click a button and say, okay, I want this to make me more attractive. Now, we can put aside the issue of sort of why you'd want to do that and sort of the ethical challenges of that, of wanting to make yourself more attractive before putting it up on the web, et cetera. And what does it mean to make somebody more attractive? We'll put aside those issues. But one of the things that it turned out this model was doing was actually manipulating your skin color. So for example, making your skin lighter as a way of making you more attractive. And this then raises, of course, a number of questions about, okay, so what has it learned about the attractiveness of different people and people of different skin color? Like, what does it mean that this model is sort of implicitly prioritizing people of certain skin color versus others, and sort of claiming that some of those are more attractive than others? And kind of around that time, there started being, a lot more questions, right? So machines taught by photos learn a sexist view of women. I'll talk a little bit about that later on, but basically learn to associate women with particular types of activities and men with particular types of activities, sort of stereotyping men and women into different stereotyping into different categories in ways that were actually even stronger and more problematic than just what was captured in the data. Like, obviously, what was captured in the data is some of the reflection of our world and the different roles that men and women tend to play in our society. But then the models were actually learning a much stronger and more stereotyped view of this. There's the work, which I'll talk about a lot more later on, about how facial recognition is accurate if you're a white guy. So this was work that sort of showed that computer vision technology deployed by three top companies in the US was actually sort of very accurate in pictures of white men or pictures of men with lighter skin. This was less than 1% error rate versus when you showed pictures of darker skinned women. So pictures of Black women, for example, it had something like 15 or 16% error on those faces. And then, more and more, so sort of cropping algorithms. This is on a social media platform when faced with a photograph with two people, and it's sort of choosing one to kind of highlight as the as sort of the thumbnail for this post. It was preferring lighter, slimmer, and younger faces. So there's tons and tons of literature out there that talks about this, and I highly, highly recommend these if you can get some of these books or some of these. So Algorithms of Oppression is a book by Sophia Noble talking about search engines and some of the biases in search engines. Race After Technology is a great book that came out in 2018 by my colleague here at Princeton, Professor Ruha Benjamin, that talks about sort of some of the racial biases and systemic biases in AI technology. Coded Bias is a documentary. It's available on Netflix. Sort of again talking about some of the biases and some of these issues in the technology. So what's, if we're talking about this from a more technical perspective, right? So how are where does some of this bias come from, right? So why is this happening? Obviously, nobody wants to build a model that sort of discriminates against some people, or at least in general, you probably the AI researchers did not intend for that to happen. So why does this happen? Why do some of these biases make their way into the system? So the first kind of takeaway, the first tidbit, is when we're talking about data, it's that large scale does not necessarily mean equal representation. So just because you have access to millions of images to train your model does not necessarily mean that this is an equal representation of sort of everybody around the world, or an equal representation of all of the people you might want to capture in this data. So, for example, the work on gender shades that sort of talked about the disparate accuracy rates of face recognition technology. So one of the things that they noted is that there's an imbalanced distribution of skin color in face recognition data sets. So the data sets that were being used for training face recognition models, at least sort of in academia, many of these data sets had 80 to 90% of the faces in there were faces with lighter skin. So then it's not surprising to some extent that when you train a model on this data, you get models that perform very well on people of lighter skin, perform less well on people with darker skin. Similarly, you can look at data sets like ImageNet, which is one of the large scale and sort of core data sets in computer vision models. So you can look at sort of skewed demographic distribution as well as cultural associations in ImageNet. So you can look at, so here in the graphs, you're showing on the x-axis, this is synsets, which is basically a fancy word for classes or for object category in the data set. And y-axis is the percentage. You can look at gender, so sort of male or female, or unsure on some of these images. So unsure, for example, the class that you see with a lot of unsure categories. So this was a class of scuba diver. So this was people wearing sort of scuba suits. And so it's hard to tell whether they seem to be male or female. But, in general, in the data set, most of the people appear to be male. You can look at age distribution. So again, you see most people in this data set seem to be sort of young adults. A little bit more adults 40 to 65, and then very, very few sort of seniors, very few people over the age of 65. So then, as you might imagine, when you're training models on this, they might work well on younger people, but would not work well on seniors, for example. And then if you look at sort of particular categories, so for example, the category of groom, so if you look at the photos in there, so it's depicting a very particular image of what a groom looks like. So it's somebody in a suit. This is a pretty, this is what a lot of like US weddings look like. These are the kind of dresses that people wear. This is the kind of suits that people wear. But around the world, people are getting married everywhere, and what a groom looks like is very, very different in different parts of the world. And so again, when you start looking at like what is actually captured in this data set, you realize that what is captured are patterns that are very specific to certain countries or certain regions of the world, rather than being more representative. You can also, in more detail, you can look at like gender representation, again, an association captured in COCO, which is another data set. You can look at the different types of scenes. You can look at the fraction of images within the scene that contain people who are male or female. So for example, you can look at the scene at the bottom there of shopping and dining. You can see that sort of there's a lot more females in that scene than males. You can look sort of about a third of the way down at outdoor sports fields and parks. There's a lot more males and females who are depicted as playing sports. And perhaps digging a little bit deeper, you can even see things like, well, so if you look at pictures of people present with flowers in this data set, so there may be, a lot of men represented with flowers, a lot of women represented with flowers, but actually when you look at sort of some of the extreme images of like, okay, what are the images that are represented with women and flowers in this data set? Some of these are sort of highly stylized images. And when you look at images of men represented with flowers, some of these are sort of men in conference rooms with flowers, on the table. And so even though some of these correlation statistics may be, may not sort of show some of the deeper bias that exists in the data set, or some of the deeper sort of patterns that are captured in this data, you might be able to see some of these by looking specifically at the images. So, okay, so what can be done about this? So this fact that like, okay, not everybody's represented in the data set. So first of all, you can know your data, right? You can ask these questions. You can ask like, is this a problem? Because one of the things that often arises, like, is that a problem that women are more represented in shopping and dining scenes because like, maybe that's what they do more of. And this is a question that sort of we have to ask about each data set. I don't have an answer to this now, but what I found in a lot of the research, you sort of think that something is, you basically you don't realize that there's any kind of like you don't know what patterns are in there, so you don't have the ability to even ask these questions. And sometimes you find this pattern of like, well, most images in my data set contain sky, or most images in my data set contain lighter skinned people. And you're like, well, that's not a problem. Like my country primarily has people who are lighter skin. I'm building this model for my country. Like I don't see a problem with that. And that's great. If you don't see a problem with that, then that's totally fine for your use case. Like this is not an issue. But a lot of the time when we're building these models, we sort of pretend like they are universal, that they're going to apply in all settings, and understanding that they don't understand what's hiding in the data can be very helpful and sort of very powerful to be able to understand the limitations of the technology. You can collect more representative data sets. And I'll talk about that a little bit more in a second. You can design algorithmic interventions. You can say, okay, now that I know that my data maybe is not perfect, I can think about how to sort of fix this or mitigate this when I'm building the model. Of course, you can also sort of move away from reliance on data, but that's actually we don't know how to do that now. Maybe this is part of future, AI, future AI research. Maybe this is something that some of you are working on, but like right now, we don't really know how to do that. A lot of the technology is relying on the data. So let's talk just a little bit about some of these like algorithmic interventions. I'm not going to go too much into the technical details, but I'll give you, some of the papers that you can follow if you're sort of curious about that. So one way of thinking about these algorithmic interventions, you can think about sort of algorithmically mitigating correlations in the data. So the setting could be something like, okay, so you have a data set that correlates some target label, so something that you're trying to predict. So for example, like whether the person is performing a particular activity, it's correlating that with some protected attributes. So for example, the person's gender. So you're trying to, understand whether the person is cooking, and cooking is very highly correlated in the data set with women. So this is one of the earlier works. This is what inspired that headline of like machines learn as a sexist view of women. So this is that work that sort of is trying to predict on photographs whether the what activity the person is performing, and the activity of cooking, for example, is strongly correlated with the person being a woman, or sort of looking like a woman. And then the model actually learned this very strong correlation between, so it would basically only predict cooking when it saw pictures of women, and similarly, whenever it saw a picture of somebody cooking, it would assume that sort of this person must be a woman because they're cooking. And so the goal could be to develop a method for training visual classifiers that would actually ignore such correlation, if the correlation is deemed sort of unnecessary and or harmful, if this decision is made that you want to either ignore this correlation, or at least if you want to sort of not let it impact your predictions. And there's a number of works. I'm highlighting sort of two that came out of my lab specifically here. So one where we tried a number of different methods where, for example, you can rebalance your data, right? So if you know that you want, you have a lot more pictures of women cooking than men cooking, you might say, okay, so that's fine, but I actually want to rebalance my data such that these are, represented equally when I'm training the classifier. Or you could think about, I'm going to train a model separately for pictures of women to classify activities, and then separately for pictures of men to classify what activity they're doing. And I'm going to apply those two independently such that, I can hope to make sort of more accurate predictions that are not as influenced by the particular correlations. So we sort of run a number of analyses of that type. And then a different approach, which is basically where we started looking at generating data. So the data is imbalanced, but you can think about like, well, given, and this was done in 2021, now, the generative models are even more powerful. So you can think about like, oh, so I might be able to generate some data to sort of make up for some of the missing types of images that maybe are not present in my real world data set, but I can generate some photos and sort of put that into my training data. So there's sort of a number of works like that you can do sort of on the algorithmic side to try to mitigate some of this. But it turns out, so this actually algorithmically mitigating this, so this becomes increasingly challenging in real data, kind of in very interesting ways. So one of the things is there was some work being done for a while on like adversarial debiasing. So adversarial debiasing is sort of this idea that I'm going to train a network to do sort of primary classification, which is basically, classifying, let's say, what activity the person is doing, classifying whether they're smiling or not, sort of predicting your target label, whether, somebody's cooking or not. And then you have sort of secondary classifications that kind of enforce sort of secondary classifiers in this model, where you're going to try to enforce sort of confusion. You're going to try to say, okay, but I don't want my model to learn any information about gender. So, and what I'm showing on the right is sort of the distribution of, so this is I think it's a t-SNE projection of the feature representation layer, where sort of blue are feature, so this is the embedding layer, the feature representation of images containing men. The red are the embedding of the images containing women. And so in the baseline network, when you're just training to, let's say, predict cooking versus non-cooking, the embedding learns sort of to project pictures of men and pictures of women in sort of different parts of this embedding subspace. But when you add this like confusion loss, when you say, okay, actually, I wanted to be able to predict the activity, but I don't want it to actually learn information about the gender of the person in the photograph. So then by sort of adding this adversarial training, adding this extra confusion loss, you can train a model that sort of creates an embedding space where the photographs of the two genders kind of are all intermixed together and are not easily separable. So this kind of approach seems to be very promising in theory, but it turns out that in practice, when we are looking at sort of understanding how pervasive visual gender cues are in modern data sets, so it turns out that they're really kind of everywhere. So if you look at some of these photographs, these are photographs from the COCO data set. They have tons of different scenes, tons of different sort of people in real world contexts, doing all kinds of things. Some of these are close-ups, some of these are far away shots. So if you actually look at sort of photos of men, women in these scenes, they're really, really different. So even something like the average color of the photograph can actually give you a hint as to whether this person is likely to contain somebody, is likely to contain a man or woman. Because, for example, in outdoor scenes in this data set, there's a lot more men in outdoor scenes. So if you see that the average color of the photograph is green or blue, it's actually more likely that this is going to be a photograph of somebody who's a man. Whereas if there's a lot more women in like indoor scenes, so if you see that the average color is brown of the photograph, it actually signals that there's more likely to be a woman in the photograph, which means that, and we have, a paper sort of diving into this a lot more details, but it actually means that some of these sort of adversarial approaches of trying to not learn any gender cues while learning, to predict things about the photograph, it becomes essentially impossible because the gender cues are so pervasive. Now, again, this is not necessarily a problem, right? You can sort of, again, we're kind of coming back to this idea of like, well, people are doing, people of different genders, like men and women are doing different things in society. And like, maybe that's okay that our models are learning that. But then again, we have to sort of be aware that first of all, our models are learning these facts. And second of all, the models, this is when we come back to the idea of like bias amplification. It's called bias amplification, which is like, to what extent are the models learning patterns that exist in our society versus to what extent are they actually amplifying those patterns? And a lot of the work in like AI fairness now, we're not even trying to like remove any of these stereotypes. We're actually trying to like make sure that the models are not amplifying any stereotypes, like any biases that actually sort of exist in the world. Okay, so the sort of final tidbit here that I want to say about the data is that sort of algorithmically mitigating bias in the data actually becomes impossible when data is simply missing. And so if you look, this is where I'm going to talk about sort of geographic bias and geographic distribution in these data sets. So sort of putting aside issues of gender and saying, okay, supposing, I'm not training a model that's learning anything about individual people. I'm training a model for recognizing objects and photographs, right? So I just want to recognize, common household objects. I want to build a robot that can help me around the house. I want to build, some system that can automatically classify, my photographs into photo albums, whatever I'm trying to build. I just want to recognize objects. And so this has nothing to do with any kind of social bias, with any kind of fairness questions. Okay, so it turns out that when you look at common computer vision data sets that are being used, and you look at the GPS tags of those photographs, and you ask, where are these pictures coming from? So on the left is a map of the world, and you can see where these pictures actually being collected from. So primarily in these modern data sets that are being used by all kinds of sort of academic labs, by industry labs, they're primarily coming from the US, a little bit from Canada, a bit from Australia, some from Europe, essentially no photographs from Ukraine. Like you can see Ukraine, very, very few photographs, like very few fraction of these photographs are actually coming from Ukraine. And so what happens then? So there's this paper that came out, does object recognition work for everyone, that actually analyzes, again, sort of error patterns in object recognition technology that was deployed. And they found that, for example, a model may be really good at recognizing US brands of liquid soap. So in the US, people use primarily sort of these like liquid soap bottles where you kind of pump the soap and you get some like liquid soap on your hands rather than bar soap, which is what's used in the vast majority of the world. And so you look at, the predictions of these models and you realize that its concept of soap is actually these like US brands of liquid soap rather than bar soap. So it's like not recognizing. So I think for this picture, which is like very clearly a picture of soap, it was predicting that this is some kind of food because it just like was not associated with the concept of soap. So, is this a problem? Well, if you're just building models that are supposed to work in the US, then, I mean, maybe not. There's not that much bar soap. I mean, it still exists and sort of people use it, but like not as much. Maybe that's less of a problem. But like if you're trying to build a technology that you're claiming is going to work for everybody, well, I mean, this is a very obvious thing that it should, it should work on these kinds of objects, but yet it doesn't. And so one of the works that we did recently in my lab, it was published last year, although it feels like we did it a while ago. I don't know, time it's just sort of flying in weird ways these days, but it's called GEODE. So this is a geographically diverse object recognition data set where we went out and sort of partnered with people in different countries to collect photographs for us So we collected 60,000 images of 40 common household objects. This data is publicly available. If you're interested in downloading this, you're more than welcome. We try to make sure that we get people in sort of different regions of the world that are not commonly present in modern data sets, and sort of try to get them to send us photographs of objects in their homes. I'll point out that sort of importantly, when we started this process and started sort of partnering with people in different countries, the first question basically that we were asked by the Princeton legal team, so this was around the time of the invasion of Ukraine, one of the first questions they asked is, they're like, you're not partnering with anybody in Russia, right? And we're like, no, like I am, no. And they're like, okay, just to be very clear, like you're not allowed to hire anybody in Russia. We have, no economic ties, like we, this is extremely important. We're like, no, we got this. And so we, we were very, very careful about this. And I was really glad that this was sort of front and center in my mind, but I was really glad that the first question that the Princeton legal team asked us is basically like making sure we're not recruiting workers in Russia. So in this data set, so you can look at, so for example, these are pictures of stoves in different areas around the world. So we have sort of every row is, there's pictures from West Asia, there's pictures from Africa, from East Asia, from Southeast Asia, from the Americas, and from Europe. And then at the bottom is some of the pictures of stove from ImageNet, from the sort of canonical computer vision data set for comparison. And you can look at some of these pictures of sort of single burner stoves or different kinds of gas stoves that just like are not really, you can contrast this with sort of the type of photos that are seen in ImageNet. Also the pictures in Geo, they're like household objects that are actually being used. So sort of these are, whereas in ImageNet, because these are photos from the web, sort of people uploaded these online for a particular purpose. A lot of them tend to be cleaner. They tend to be sort of more expensive type of stoves and things like that. And so by going out sort of into the wild, going out to some of these countries, reaching out to some of these people, we're able to collect sort of a much more diverse data set of objects. And so we can look at, for example, the CLIP model or some of these like large language models. Look at like, okay, how would they classify some of these pictures from around the world? And so one of the things that we, and again, in the in our paper, there's a lot more analysis, a lot more findings, but actually it turns out that, for example, CLIP classifies a lot of houses as religious buildings. Particularly houses coming from West Asia and sort of Southeast Asia, when it sees sort of pictures that people have taken like of their homes, of houses that they live in, CLIP tends to then classify these as religious buildings because it hasn't seen any of those houses or many of those as like houses, but it's seen religious buildings that look like that. And so you can see sort of some of the errors that CLIP makes on these photographs. So, when we're again coming back to sort of wrapping up this idea of sort of data, large scale does not equal representations. You can know your data, you can collect more representative data sets. It's really important because it helps both build better models, but also just reveal what's actually going on in some of these larger models. But it's quite difficult, also very expensive. So Geo, it costs a lot of money to collect that data. But also that, you can intervene with algorithms, but like algorithmic interventions have limits, particularly when you're talking about something like geographic underrepresentation. There's stuff you could do on the modeling side, but it's actually, there's types of biases or underrepresentations that are very hard to mitigate just by looking at the algorithms. So sort of, to wrap up some of these, so one of the questions that arises actually is like, to what extent and under what conditions does bias in data actually influence AI models? And sort of when do AI models learn, like what kind of bias in the data do they actually learn? To what extent can AI bias or sort of AI errors can be traced to what's happening in large scale data? And so to answer this question, we can think about this cycle, right? So there's some kind of human history or bias or prejudice or stereotype or societal norms that make its way into the large scale data, reflected in the data, sometimes amplified in the data, that makes its way into the AI models. The AI models learn from this data, that becomes part of AI decision making, and then ultimately feeds back into our human history. So as AI models start making decisions, they start sort of either amplifying or perpetuating or mitigating some of the social sort of social stereotypes or social constructs that exist. So when we think back to some of the work that I've talked about, so for example, gender and racial bias and face recognition. So this is this model that I mentioned where, so this is showing the accuracy on darker males, darker females, lighter males, and lighter females, and sort of the gaps in accuracy between those. So I already said this could be sort of somewhat traced back to the imbalanced skin color distribution and face data sets. You think about geographic bias and object recognition. So this can be traced back to sort of imbalanced geographic distribution in object data sets. And then there's sort of this question of like, when does bias in sort of large scale data set actually propagate into models? And so I'm not going to go again into sort of all of the technical details here. We have a couple of papers on this recently. And so there's sort of some partial answers. So one is that when AI model is actually powerful enough to fully capture the data distribution, this is when it sort of learns to capture some of the bias in the data. So it seems like sort of the more powerful the models get, the more accurately they're modeling the data, and then the more they're sort of sensitive to different types of biases in there. And for example, if you think of like a very simple model, like a very simple, I don't know, linear model based on SIFT features that's trying to recognize, pictures of soap, it may just, what it learns is sort of like, oh, maybe soap is like kind of rectangular shape, but that's all it kind of learns. And in that case, it's going to sort of make errors on all pictures of soap. It might not sort of, particularly learn to favor some versus the others. It's just kind of going to make errors throughout. It's going to learn some very basic features. But if you're building a more powerful model where it might really try to capture all of the details, try to be really good at distinguishing, soap from other objects, that's where all of the like intricate details of the data set really start to matter. And then the second bit of the answer is that when the data bias is actually salient or more sort of more visible, more visually salient than the model's task. So for example, when you're learning cooking, right? So to predict cooking, or you're learning to predict, some kind of activity. So if the visual cues for that activity are themselves very, very salient, then the model doesn't actually learn to rely on, gender cues or any kind of additional correlations. It just really focuses on this particular activity and learns to be really good at recognizing it. But when the activity is sort of more, when the task is like more subtle or more complicated, that's when the model sort of starts picking up on auxiliary cues and what's called spurious correlations. And that's when it might learn some kind of biased representation. So, coming back and sort of wrapping up this question of like, I talked about sort of data, but data tightly connected with models and tightly connected with some of these human questions of like what is actually happening in the data set. So just to kind of wrap up here, right? So who are the humans involved in the data set? Besides the humans that are interacting with this technology or being affected in the technology, it's important to remember that there is a number of people who are actually sort of influencing this data, influencing this technology. So for example, the subjects, right, in the photographs, right, who is represented, how are they represented? There's also questions of like, did they consent to be included in this data? The photographers, right, so what was their intention in taking the photo and for what purpose did they share the photo? So a lot of the time this is, photos on the web are more staged, or they're taken of, cleaner objects, or they're taken, for some kind of purpose of, and so is that the kind of data we need for, different applications that we're building computer vision models for? You can also ask, of course, sort of the more legal or ethical questions about the photographers. Do they know that their data is being used? For the data annotators, so sort of who are they? Who's labeling this data? How did their social lens or their identity or their culture actually factor into the annotations? Also, were they paid a living wage? Are we sort of actually compensating these people for the like really important work that they're doing for the AI community? Lots and lots and lots of papers here that sort of dig into some of these issues if you're curious, and I'll share the slides afterwards so you can follow up on any of this. And then, of course, I said we're not going to talk very much about like the AI research. We're talking about humans beyond AI researchers, but I do want to conclude by like talking for just 2 slides here about who are actually the AI researchers. So there's a lot of statistics out there and a lot of conversations. Sort of, this is a growing topic. I'm delighted to see that this is a growing topic in the community of like, who are the people who are actually in positions of power to build these systems? And so by some statistics, right, it's about 16% women, about 84% men, right? So a lot of this technology now you can argue that, maybe there's different reasons why women are not, including, or why they are not, maybe they don't want to do AI research. And this actually turns out to be not true. There's lots of studies that sort of show that this is not the case, that they don't want to do AI research, but there's a lot of reasons why they're not being included or welcomed into this space. You can look at sort of demographic distributions of folks who are white, who are Asian, who are Black. How are they sort of represented among AI researchers? You can read about sort of, why is this a problem? I mean, you could say that, okay, maybe this is fine, we're building sort of this technology, but like, why does it matter who's being represented, and why do we care about particular demographics? And the short answer to that is like, well, people of different cultures, people of different demographics, they ask different questions. They care about different issues. They come from different communities, from different social perspectives. And if we're trying to build technology that benefits all, we need all types of people to be involved and have a seat at the table to make some of these decisions, some of these determinations. And so one of the things that I'm working on besides sort of my work at Princeton as a professor is I'm a co-founder and chair of the board of AI for All, which is a nonprofit dedicated to increasing diversity and inclusion in AI. And so we're trying to break some of the barriers for people who may want to be part of the AI community. We're trying to find students who sort of younger students who don't see themselves represented right now among AI leaders, and we're trying to train them and support them in joining this field. We're trying to help them see a path for themselves within AI. So AI for All, we celebrated our 7th birthday, so we're 7.5 years old now. It's on March 8th of 2024, so we started on March 8th of 2017. In the US, a lot of people actually don't know that this is International Women's Day, so I have to say that, but I'm sure all of you know, March 8th, right? So this was very deliberate that we started it on this day. And our goal is to educate and support a diverse next generation of AI leaders. Our slogan is that AI will change the world. We know it will change the world. We know it's already changing the world, right? And we ask the question of who will change AI. And so we're developing educational programs at the high school and college levels in partnership with a number of universities for students from historically underrepresented groups, from students who have historically been excluded from this research. Unfortunately, we're only focusing on the US for now. We have big dreams of scaling this to countries like Ukraine, right? We have very big dreams of, we want this to go international, but for now we're still pretty small. It's been a very challenging sort of task and a lot of very difficult work and a lot of sort of difficult laws and things like that we're kind of grappling with. This landscape is changing, and so we're for now focusing on US only, but are very much looking forward to being able to grow and scale this. One of my all-time favorite quotes is this: a student who participated in one of our programs in 2016 who said that, "Until this program, I never thought that people who look like me could succeed in computer science and AI." I think this is a very powerful statement. This is something that we're looking to break down, that sort of the way you look should not matter for whether you're able to succeed in this field. There should be role models and mentors and people who support you entering this important field and allowing you to do research and to sort of do the work that you want to do in this space, regardless of how you look. And so with that, I will conclude, give a shout out to all of the students in my lab who participate in a lot of this research work. I'll put up some takeaways, right? So computer vision is, I would argue, is no longer about just models or even models and data. So it's really this intersection of models plus data plus humans. In the current era, computer vision researchers and engineers and developers have to think about and grapple with the social issues around computer vision systems. Some of these AI fairness questions are really hard, but actually really interesting. There's lots to be done, both on the technical side and sort of really thinking about how to build this technology in a way that benefits all communities and all societies. There are opportunities for both interdisciplinary work, so connecting with social science, with psychology, with sociology, with political science, with humanities. So lots of opportunities for that kind of work, but also some core computer vision work on like algorithmic bias mitigation for AI fairness. And then finally, we really need to have a broader range of backgrounds and perspectives represented in the AI field in order to get this right. So I'll pause here. Thank you all very much again. Yeah, thank you for being here. Happy to answer questions.
Thanks a lot. So it's time for questions. Please, you can write your questions in Q&A section, or you can just raise your hand and say it out loud. And I have the first question. What fairness metrics do you consider most effective for evaluating visual recognition systems, and how do they differ from traditional accuracy metrics?
Yeah, so that's an excellent question. So I actually have a paper under review right now where we sort of argue about like different kinds of fairness metrics and which ones are more effective. So I think the first answer to this is that, of course, so no fairness metrics are perfect, right? So there's many different metrics, there's many different arguments for sort of, should it be a metric about oh no, I just stopped sharing. Okay, sorry. Suddenly my whole screen was my slide. So I was like, oh, did I get bumped from Zoom? So first of all, so you can compare like accuracy rate across different groups, for example, or things like that. But then there's arguments about like, is that a fair comparison? So my argument is that you need a lot of different metrics. So for fairness in particular, what you should be looking at is a table of different numbers and different metrics. You can't say that one system is sort of more fair than the other, but you can say that like, okay, let's get a deeper understanding of what the system is actually doing, such that when I link it to my downstream application, right? So if your downstream application, again, is just, identifying, faces among, Ukrainian population, like, does it matter that it doesn't work very well on people who aren't Ukrainian? Well, no. And does it matter that it doesn't work very well on people of other ethnicities or other backgrounds? No, probably not, right? If this is sort of your default application, then some of these fairness metrics that makes it so that they don't apply. They're not. It's not a problem for this particular community. How does this differ from accuracy metrics? So I think you can sort of make the argument both ways. You can make the argument that ultimately it is just an accuracy metric, but I think one of the ways in which it differs is sort of the much tighter connection to sort of social aspects. So you might, for example, say that like, well, I actually sort of really care about it performing better on some groups, or I care about like not making particular type of errors. So you can sort of help define the type of errors that are sort of more harmful or less harmful. And then, you can think about sort of fairness evaluation, this sort of bleeds into like ethical evaluation. So you can ask questions that are not just numerical questions, right? So you can sort of move from sort of the pure quantitative questions to like questions like, okay, should we be building, face recognition technology at all? And like, what does it mean that face recognition technology is being deployed, and so sort of how, and so some of these like fairness questions kind of bleed out from the quantitative metrics into more sort of qualitative or socially driven analysis.
Thank you. Dear colleagues, any questions? Okay, I have one more. Yeah, please. I see a hand. Philippa, please.
Hello, I would start my lecture now in a minute. Hi, my name is Philippa, and I would like to write my thesis on AI. That was why my supervisor recommended this video for me. And according to what you said today, I can understand the theory. However, the practical of how this is actually implemented, example, the programs that would actually make machines be able to learn data, I absolutely have no idea. So I was wondering if you have like any advice for me.
Yeah, absolutely. So there's a number of great textbooks, for example, on computer vision. So I can put it in the chat. So one of these is a book by, so it's publicly available. It's a book by so it's a book by Rick Selesky, textbook on computer vision. So let me actually just quickly, if you give me a second, I'll actually find sort of the actual link for it. Sorry, my computer is being a little slow. Let's see, book. So this is, I would recommend, so this is a book that I use in my computer vision class, which is like a great place to start. It was recently updated, so it has some of the latest models. So the latest version is 2022. So it actually it's very, very good, and you can download yeah, so on the website there's sort of a download link. It's in the second paragraph to download an electronic version of the book. Please fill in your information, and they just like, I think, emails you a PDF or whatever. So I highly recommend that, particularly because it's free and then online. So that's a great place to start with learning, like, how are these systems actually being built, and sort of how to go about that. Yeah, it's a complicated topic, but that's my like best go-to resource for that.
Thank you.
Yeah, and I'm delighted that you want to write a thesis on that. Good luck. I think that's most excellent.
Thank you. And also, you spoke about a team that is trying to find young people, example, high school students or college students who are actually interested in AI. And I would like to know, is this like only for Princeton University, or other students from other universities can also be part of it?
Yeah, so it's definitely not just for Princeton University. It's a US-wide program. So it's called, so I'll also put this in the chat. So it's an organization, AI for all.org. So we're a nonprofit organization. So we offer both. So I mean, so there is a program running right now for students at Princeton University. So for 3 weeks for high school students, but in general, AI for All runs educational programs for college students. Unfortunately, only US for now. We're working on it. But yes, it's open to a number of students. Yes.
Okay, that was all. Thank you.
Yep, absolutely.
Thank you. Another questions? Okay, then I have one more. How do you count intersectional biases? For example, race and gender, for example, combined. And actually, what additional complexities they introduce?
Yes. So this is an excellent question. So we have a paper actually that I'll also actually just put in the chat. That sort of looks into this, that we like archive link here. So we sort of asked a number of questions of, like, with intersectional fairness. So what does this how do you go about sort of measuring that? The kind of key issues, right? So one is just, you get into a very small group. So how do you like evaluate on intersectional fairness when there may be, very few examples of Black women who, come from like Black Ukrainian women in your data set, and you might want to make sure that the model works well for them. But like, you start going, more and more fine grained. So one of the questions is like, how do you compensate for this very small data, both in training and evaluation? It also brings up like very interesting questions about privacy, because one of the things is like, when you start going to like detailed subgroup, or like you're looking for somebody who is you're like making sure it works well on people who are like in wheelchairs or with a particular type of like physical disability, right? So then you start going again very, very fine grained, and then sort of some of the with the privacy protection, there's kind of safety in numbers, but now when you're looking specifically at these kind of categories, you might be looking at like individual people. So then there's of course questions of like, how do you define these groups? And so of course, no definite, the sort of partition to men and women is not a perfect partition. There's gender is really a spectrum. There's all kinds of people who sort of identify as non-binary, who don't fit into these gender binaries. And of course, when you start talking about race, or you start talking about culture, you start, I mean ethnicity, like all of this is very, very detailed. So how do you sort of balance wanting to make sure that everybody's represented, with the fact that you know, some of these categories are very fluid. And this is part of where, you know, back to your original question about like sort of where do the metrics break down. So this is one of the places where it breaks down, where it's sort of like all of these categories are very ambiguous. And then you know, we sort of ask also questions about like metrics, because a lot of the time the fairness metrics, it compares sort of the majority group with the minority group. But when you have many of these groups, like how do you actually evaluate whether the model is sort of doing well across all of them? Like what should be the right metrics? And also thinking about things like it's actually interesting that a lot of the, I mean, it's interesting and troubling that a lot of the machine learning technology, when you look at like, when you measure fairness across, you know, many different domains, many different types of target tasks. So it turns out that like more often than not, you know, if you ask like between lighter skinned men, lighter skinned women, darker skinned men, darker skinned women, like which group is sort of going to be like underrepresented, undersampled, the models are going to perform worse on, it's basically always going to be like in the current models, it's like you see that sort of Black women are the ones who are where the models are underperforming. And this is across, you know, computer vision tasks, across like natural language processing tasks, across, you know, like tabular data that predicts, you know, health outcomes, whatever the case may be, like this is pretty consistent. And so one of the things is like, how do you capture that fact, and how do you not treat each of those categories sort of independently, but actually realize that there's some categories that are consistently being left behind? And so an algorithm that like is able to bring up you know, accuracy, brand performance on some of those groups, like that actually can be really, really meaningful sort of in the broader ecosystem of AI technology, not just for this particular task.
Great, thank you. So if we don't have any other questions, thanks a lot for your time. Thanks for being here with us, and thanks to all our participants that they find the opportunity to join. Before we finish, I want to make a short announcement about the next event, which will be on 15th of August, and we'll have Chang-Woo Kim from Carnegie University, former vice president of Samsung Research, and we'll talk about advances in on-device speech recognition and natural language processing. Thanks again, Olga, for being with us today.
Yes, thank you so much for having me, and thank you for organizing it. It sounds, I mean, the next event sounds really, really interesting.
You can join us.
Very cool. Thank you.
Okay, thanks a lot, and have a nice day. And
Thank you. Thank you very much.
Yeah.
Bye, everybody.